Reactivity at carbonyl-carbon. The reactivity of carbonyl compounds is due to the polarity of the carbonyl group, which results from the electronegativity of oxygen. So this oxygen right here is electronegative, and therefore this carbon right here is said to be electron deficient, and therefore it's going to act as an electrophile and can be easily attacked by a nucleophile. So when a nucleophile goes and gets added to the carbonyl carbon of the carboxylic acid derivative, the weakest bond in the molecule is going to break. So let's say this is a nucleophile. So when this goes and attacks this carbonyl carbon, the weakest bonds in this molecule is going to break. So obviously we do have a pi bond. So the pi bond is, since the pi bond is the weakest bond here, that is the bond that's going to break and it's going to move towards oxygen. Right? So let's write down the structure we'll be getting. So now this oxygen is going to have an extra pair of electrons, and you're going to have Y and as well as Z. Now this structure right here that we are seeing is basically the tetrahedral intermediate, because this carbon right here is now sp3 hybridized. So to begin with, it was an sp2 carbon, but now it has been changed into sp3 carbon, and we know that the shape around the sp3 carbon is going to be tetrahedral. Now this tetrahedral intermediate is really unstable. It is just an intermediate. So this is a tetrahedral intermediate and it is unstable. It's not the final compound. This unstable tetrahedral intermediate will try to form a stable compound, for which these electrons need to come in here to form the double bond, and one of these groups, either Y or Z, needs to leave from this tetrahedral intermediate, right? And which of these groups is going to leave, that is going to depend on the relative basicities of these two groups, Y and Z. Now let's look into the three different scenarios to find out which of these groups is going to leave. Let's take a look into the first scenario. The first scenario is when the incoming nucleophile Z is a stronger base than the base that is present in the reactant, which is Y. So Z is going to be a stronger base and Y is a weaker base. So this one right here is a stronger base and this is a weaker base. So let's say that Z is going to go and attack this carbon, right? This is electrophilic carbon. So the Z is going to go and attack this carbon, and the oxygen is going to take those extra lone pairs of electrons from the double bond as this bond breaks. Let's write the tetrahedral intermediate. So here is our tetrahedral intermediate, and of course this is unstable, right? It has to form a stable product, more stable product. Now because it needs to form the stable product, these electrons need to come in and one of these groups need to leave, right? And here, since Z is a very strong base, it's not ready to leave. And therefore Y is the one, it is Y's turn now to leave, right? Because remember, the weak base is going to be a better leaving group. So weak base is a better leaving group. Now what you can see is it has totally formed a new compound. So from here it has been converted into another carbonyl compound, right? So whenever the incoming nucleophile is going to be a stronger base than the base that is present in the reactant, it's always going to lead to a new product. So this reaction where a nucleophile is getting substituted for the weaker base is called as the nucleophilic acyl substitution. Nucleophilic acyl substitution, or you can also call this as acyl transfer reaction. But most frequently it is called as nucleophilic addition elimination reaction. So it's called as nucleophilic addition elimination reaction. Now, what is the reason why this is called as nucleophilic addition elimination reaction? To begin with, the nucleophile is getting added to the system to form the unstable tetrahedral intermediate, and then one of these is going to get eliminated, right? So because of which it is called as nucleophilic addition elimination reaction. Let's go on to the second scenario. Now, if the incoming nucleophile Z is going to be a weaker base than the base in the reactant, then there's not going to be any new compound that will be created. Instead, the reactants will be reformed. So again, it's going to go through the same tetrahedral intermediate, but this time it would be Z's chance to leave from the system. So let's do the mechanism for this. The Z minus is going to go attack this electrophilic carbon, thrust these electrons onto oxygen to form the tetrahedral intermediate. And once the tetrahedral intermediate is formed, of course, it is unstable. So these electrons will come in here. And now it would be Z's turn to leave, since this is going to be the weak base. Z is the weak base here and Y is the strong base, and therefore it is not ready to leave. So this is a good leaving group. Okay. So when we do that, let's see what is the product that you're getting. Obviously, it is going to be our starting material. Right? So this is basically the starting material. Now let's say that two groups are going to have exactly the same basicities. So in which case, both the products, both the reactants and as well as the products are going to be formed. So here in this case, the Z minus is going to go and attack. These electrons are going to go to the oxygen. So in which case, again, the tetrahedral intermediate will be formed. And as these electrons will come in, both of these have the possibility to leave. So the Z can leave and the Y can also leave. Right? And because of which you can get two different products. One is basically the product and the other one is the reactant itself. So you will get a mixture of the reactants and the products. Now let's see how the nucleophilic addition elimination reaction of the carbonyl compounds is different from the nucleophilic substitution reaction of an alkyl halide. So let's say that this is an alkyl halide. So when the nucleophile comes in, it's going to go make a nucleophilic attack on this electrophilic carbon. So we know that this carbon is electrophilic because you have an electronegative atom, right? And here, this is the bond. This is the sigma bond that is breaking, right, to give us a new compound. But in a nucleophilic addition elimination reaction of the carbonyl compound, let's say that this is your reaction, right? Here, as soon as this nucleophile comes and attacks this electrophilic carbon, it is the pi bond that is breaking, right? While here, it is the sigma bond that breaks. Here, in the nucleophilic addition elimination reaction, it is the pi bond that is going to break to give us the compound. So that is the basic difference between this nucleophilic substitution reaction of an alkyl halide and the nucleophilic addition elimination reaction of the carbonyl compound.